Okay, it's time to start the rotational mechanical systems, which, quite frankly, it's very analogous to the translational, as we will see. Okay, uh, unit-wise, we're moving from force to torque, rotational versus translational. We had position, velocity, acceleration. Now we're going to have in radians per second squared. Angular position, angular velocity, angular acceleration. Mass moves from mass as we know it to mass moment of inertia. So very similar. We have rotational dampers. So we'll do them relative to velocity the same way. So here's our damping constant and then the relative velocities between going from one side of the damper to the other. And spring is the same thing, except it's based on angular position. Now, the thing we get to add into this problem are gears. So, when we go to model these, we are going to look at gears as having no inertia, so mass, which means they're massless, no stored energy, no friction, perfect meshing of teeth. So, when you go to look at a gear, uh, the radius of the gear will be proportionate to the number of teeth that they have. The number of teeth will be an integer number. So here we have two different size gears. The bigger gear has greater radius, more teeth. Common sense. And then when we look at how they run, okay, so if I have this gear turning, say, counterclockwise, that makes this go clockwise. And they have different angular velocities, but what must be the same? The velocity of the teeth as they come together, they absolutely have to be the same. So this one will be spinning slower, this one will be spinning a lot faster, but this has a smaller radius, this has a larger radius. So R omega 1 must equal R omega 2 right here. The velocities, they have to be going together or you're ripping teeth off these things. So we know the velocities have to be the same, but the forces between the gears have to as well. Keep in mind, we're treating these things as massless. So if something is massless, the sum of all forces equals ma, m0. This is sum of all forces equals 0. The same applies to torques, all right? So, but at the end of the day, you've got a tooth here and say a tooth here, and if this gear is driving that tooth and it's applying a force in this direction, but this gear is going to oppose it and it'll force back in the opposite direction. And how do you look at that? Well, it's this simple. You've got a force from this gear to that one and this one to that one, but look at pretend there's a little mass in between the teeth. So where these forces are happening, that there is no mass there. So again, sum of the forces equals 0. So F1, the force to this gear, and F2, the force back to this gear, the sum of forces must equal 0. These forces are the same, opposite directions. So what you have here is the torque in these will be different. So you have the forces are the same, but the radius is different in each of the gears. So the torques are not equal. All right, but that's the beauty. I mean, that's how your car transmission works. By switching to different size gears, you can increase the effective torque, right? And so that's how your car runs more efficiently. So here we have our keys. The velocity of the meshing teeth must be equal. The forces pushing against each other, there's no mass there, so as a result, sum of forces must equal 0. All right. And then we have the notion of the gear ratio, uh, which you should have seen in your kinematics course. So velocities are the same. R1 omega 1 must equal R2 omega 2. And that megas are proportionate to arc length and angular position. So we have, looking at it this way, is whatever position amount this spins out, this one must do the same. So R theta 1 equals R theta 2. Gear ratio is simply defined as the ratio of R2 to R1, in which you can Basically, so in this case, so we're having energy go from, basically through here to there, as it were. So we have our gear ratio R2 over N1, R1, and that'll be equal to the number of teeth on the second gear divided by the teeth on the first one. And you can define these in either ratio, either direction. All right. Now, notice that here we have R1 omega 1 equal R2 omega 2. So here's R2 R1. That means when you bring this over here to get R2 on R1, you're going to get theta 1 on theta 2. Okay, so the order is going to flip. And of course, if you have theta 1 on theta 2, you have the ratio omega 1 on omega 2. So when you look at gear ratio, it's radius or gear teeth of one versus the other, and that will flip relative to angular position or angular velocity, as you see there. All right, the fact that the forces are the negative of each other, it means we have the forces are the same, but then when you multiply through, you get the torques are different. So T2 equals minus N T1. The negative has to come in because you change directions here. Which direction this rotates in, this is going to go in the other way. So these things are all reasonably understood. And we're going to look at, let me just look at one more part. So in terms of the parts we have to look at to pull this off, pulleys. When we look at pulleys, we will look at them as being massless, which means they have zero inertia, that there is no friction in the pulley either at the hub or around the outer wheel. Massless, and then relative to the rope, it is massless and it is inextensible. It could be a belt, rope, chain, cord, probably some other words could fit in there. But the idea is, since everything is massless, then you must have the force here equals the force there. The sum of forces must equal zero. So if the forces are the same on each side, it says the torque effect through here is zero. All right, so those are the parts. We will start looking at problems here next.